to I better wait for that to happen. Welcome to Virtual Night Sky. My name's Rick Alling, and I'm going to be your host tonight. We've got quite a little program for you. Our programs, as you probably remember, if you've been watching us before, last about an hour, and in tonight's program we're going to really focus on a new subject we haven't done before. It's the study of exoplanets, planets that are around other stars. And for that I have a guest that I'll introduce in a little bit, and she is Dr. Jenny Patience. You'll meet Dr. Patience and learn a little bit about exoplanets tonight. I also wanted to sort of suggest that this is, if you're new to this particular broadcast, we do this every other week. We call it Virtual Night Sky, and it is a product of the Community Outreach Group for the School of Earth and Space Exploration at Arizona State University. This particular program started about 2 years ago, and we've been doing it every other Wednesday ever since. And it was really a COVID answer to staying connected to our community and staying connected to our friends, but we've kind of turned it into something that we like. It's regular. We have regular viewers, and we have new people that join us every week. So if you're one of those new ones, welcome, and we want you to sort of learn what we do here, and then maybe come back and join us another time in the future. I want to introduce the team that makes this happen. So you might have had a communication from Kim Baptista. She's the webmaster, and she's the one in controls of how to get these notices out and how to get these things programmed, putting the web format together. And so I thank Kim for her diligence and doing that for the entire term of our 2 years. Meg Hufford is my colleague at the School of Earth and Space Exploration, and she and I actually are in charge of visitation, people that want to come visit us. I mean, we have remarkable facilities, and there's all these things, and because of COVID and because of the care we had to take to kind of protect our staff and students, we stopped doing public programs a while ago. We're starting to do it again a little bit. There's been many private tours and other things going on. So if you would like to come visit us, you can. Any day of the week, we are open. You can wander through. We have wonderful galleries. There's always something going on. And if you have a group and like to come visit us, please make sure you contact us. You can do it through Kim. She's your communicator. And just we can invite you to come put together a program and let your group see what we got going on there. That would be really fun to do. So we also have Alicia Hyatt. She's been with us. So she's been actually with our program for 5 or 6 years now. And she's our latest employee. She's an education specialist, and she'll be with us. She's doing part of the presentation today. Alex Blanche has been a student with us for a while, and Armin Dalla has joined the team. So that's really your group that puts this all together. A couple of technical things. We are webinar format. That means we don't chat. So there is no chat function for you, but there is a question and answer button. And if you haven't done this before, we encourage you to sort of like push the button at the bottom of the screen. And if you have any comment or you have a question, anything along the way, we read those questions as they come in. And the students are working in the background. They will sort of decide to answer them for you if it's a simple question, all this stuff. And then they select some to bring forward. So especially about exoplanets, and especially when you're listening to Jenny Patience talk about her research and what she does, this is all new material, and you might have questions about that. Please feel free to get on. That's how we can kind of chatter about this a little bit and bring your questions to the table as we go along. So let's do that. We close caption kind of as a rule. And we do that because it makes it easier for us to post these later. And but you're in charge of your own screen. If you don't like to see the closed captioning, if that sort of wants that in the background, then you can turn it off for yourself, or you can set it up so you can watch it. With that, I think I wanted to just, before we get started with the rest of the program, I wanted to kind of just remind you of our assignment from last time. We were supposed to, or I asked you if you wanted to, right? This is always voluntary, but the morning is the time to see planets. Actually, let me get kind of that view. And I'm just going to spend a little moment with this, reminding people what the planets are doing and why it's kind of so exciting in this particular time. That's your Earth, right? That's the planet we should all know and love. I suspect we do. If I sort of back out a little bit, I'm just going to kind of get way out into more of a solar system view. I'll turn on some solar system orbits so we can see that part. And I'm going to size up the planets. Planets aren't really this big in relation to each other. I actually sort of have made them bigger so they're easier to view. So here we got sort of, let me just kind of get out. I'm setting up the view as I go. I'm actually live flying this thing, and I'm not the best flyer in the world. Let me straighten things out a little bit. What I wanted to show you here is you can see sort of the beautiful arrangements of the planets just right now. The Earth is in the foreground, and it's the blue orbit, so that should be pretty easy to find. I'll get a little bit closer. And I'm going to back out in a little bit, but before I do, I just wanted to show you the inner solar system. And I want you to notice that all the planets we're going to see as I back out, and you sort of like can count all the ones that are in our solar system, they're all on the right side of the sun. And what that means in this particular view is that they are all morning objects. None of the major planets that we get to see in the night sky are actually evening objects right now. And so I'm introducing this to you for a couple of reasons. One is this is still beautiful to go out and look at the morning sky, and there's sort of people have been doing this just before sunrise, before it gets light. So about an hour before sunrise, you can go out and kind of take a look at the sky, and you can see all these planets lining up together. Mercury is the one right here, and it's moving in this direction. Let me see if I can use my pointer. I can't do it. So anyway, it's moving to the right. And so when it gets to the outer part of that white ring, it'll be the most visible, and that will happen within a couple of days. So you got some new things to work for. Mercury is a planet you just have to know where it is when you're looking. Otherwise, you're not going to find it. So we're going to sort of find it in the morning sky. Notice that Mars and Venus are kind of like right next to each other in space. And then Jupiter is out a little bit further. And then Saturn will sort of make up the scene over there. So I'm going to ask you to kind of project back again. If you are on Earth and you're looking at this scene, in order from the horizon, right? The sun is still below the horizon. In order from the horizon, you'll see Mercury, and then Venus, and then Mars and Jupiter will be very, very close to each other. About 3 days ago, they had a conjunction. Mars just moved right under Jupiter. Hopefully some of you noticed that thing happening. And then Saturn will be the one kind of up in the distant sky over continuing to the right. Again, in 2 weeks, we're going to cover this in detail. I just wanted to show you this because really this is a solar system. This is our sun and a collection of planets. They all orbit our sun. It's fun for us to watch. It's fun for us to know the history of how we came to understand the planets and their orbits, how they work, how they're predictable. And all of that stuff is a fascinating part of history. But this is a solar system around our star. This is basically the sun's solar system that we are included in. In the next section of the program, I'm going to bring Jenny Patience to the screen, and I'm going to kind of close this out. And I wanted to just sort of like, we're going to take a little moment and talk about not our solar system, but other solar systems around other stars. And we're going to talk a little bit about when these discoveries happen and who works in this kind of research and what we're studying now and how that works. And when we're done with our exoplanet section of the program, we have another couple of things to recap you on and sort of get you focused at some new things to look at in the night sky and going forward to the next 2 weeks. So let me, with no further ado, let me bring Jenny Patience to the screen. Dr. Jenny Patience. I have known her for, oh goodness sakes, about 8 years now. She teaches in the Marston Theater quite a little bit. And Jenny also is one of the only researchers, or the first one I ever met, that exclusively does exoplanets as part of her research. Jenny, are you there?
Yes. Is the video and audio working okay?
It's certain. I haven't seen it yet, so I just wanted to sort of let everybody see you first, and then you can kind of get your video going. So, and you brought with you today a couple of videos. So I think the first one you just kind of have to show us and then talk through it, right?
Okay. Yes.
I'm going to go ahead and close my video so I can watch, and there you go. It looks very good.
Okay, great. Thank you. And it's very nice to be able to describe to all of you some of the work that's ongoing at ASU and amongst astronomers around the world to be discovering and exploring the planets around other stars. So you had that nice introduction of the closest planets in our own solar system, all of those that are visible with your eye. And then what we'll do is we'll next take a bit of an exploration into planets around other stars. So I thought I'd show you a few videos to help with that. And so we'll start with a video that goes over how astronomers discover exoplanets. So we'll be, and then we'll work towards an understanding of what these images are at the bottom of the title slide. These are actual pictures of systems of planets and disks around other stars. So first we'll go ahead and begin with actually a tutorial that we put together for our ASU students. And so you'll have a chance to learn what some of our students are studying. So what we're doing is we're leaving the Earth behind. That's what you saw at the bottom of the screen. And what we'll be doing is taking a virtual visit to the first sun-like star that was discovered to have an exoplanet in orbit about it. And we'll see how that planet was discovered. So this is the star 51 PEG. Oops, oh, I'm sorry. I was trying to move the Zoom controls and that switched the video. So let me get back to this. Let's see. All right, we'll have to start over again. So here's our Earth with our own tenuous atmosphere here. And now we're moving outwards in the sky to the star 51 Pegasus. And so this is a star that if you're somewhere dark, it would be just visible with the eye. So it's right about the limit of what the eye can see. And so as we virtually visit this system, what you'll notice is we'll bring the star into the center, and then faintly off to the side, you should be able to see our simulated planet, and it's now moving in its orbit about the star. But that is not actually how the planet was discovered. The planet was discovered because if you look carefully at the system, what you also see is that the star itself is moving, because actually the planet and star are both orbiting about what is called the center of mass. And so as the star makes this small amount of motion, if we as astronomers take a spectrum, that's what you see down at the bottom, what we'll notice is that the what are called the absorption lines in the spectrum of the star, we'll see those moving back and forth. And by actually monitoring the system and measuring those back and forth motions of the star itself, then we're able to infer the presence of this unseen object, the planet around the star. And then the time it takes for those variations to occur, that tells us about how long the orbit takes. And next we'll be going to visit another planet, or I'm sorry, another star about which an exoplanet was discovered. And this planet was discovered through a different technique, and we'll see how that works. So again, this is an indirect discovery of an exoplanet, and we'll see how what is called the transit method works. So again, we have our simulated star. Now we're going to be in the reference frame of the star, so it's not moving, but the planet is moving about it from its perspective. And what you notice is that in the course of the orbit, there will be periods of time when the planet actually crosses in front of the star as viewed from the Earth. So now what we'll do is we'll simulate what an astronomer would measure. With a telescope, all we need to do is measure the brightness of the star. So you'll be seeing a little strip chart cartoon, and you notice a steady brightness until the planet crosses in front of the star. And then you see this drop in brightness. And by, again, carefully monitoring the star, those drops in brightness, those brightness dips, the amount of time it takes between each dip, that tells us the period of the orbit. And then how low the brightness of the star drops, that tells us about the size of the planet that is obscuring the light of the star. So those two detection methods have discovered the overwhelming majority of systems. And then another way is perhaps what you thought might be the way astronomers find planets, to take an image. So we're seeing an example, a little simulation of a standard image. Now, if you use specialized equipment called adaptive optics, you'll see that the image has been sharpened up to a tighter point of light. This is an example of imaging a star. Now, if you also add a component to block out the light of the star, that makes it more accessible to view faint objects around their stars. And so what we'll be visiting now, our little virtual trip, is to visit a system that was already known to have rings of dusty material around the star. And then with this specialized form of imaging with adaptive optics, astronomers, and this is a project that students and I were involved in, it was possible to image the planet. And now here you're seeing the actual research images of this light being detected directly from the emission of a young giant planet around a star, in this case, somewhat more massive than the sun. And so that gives you an indication of three of the main ways we discover exoplanets. So how many are out there? This gives you an example snapshot. If you were to look out into the sky, all these nearby stars with circles around them, those are known to have exoplanets, all these colored stars. And then if we have now a galaxy-wide view, what you see is that there's only a small piece of our galaxy that has so far been explored to search for exoplanets. And it gives you a sense of all the discoveries yet to be made if we were able to really survey our entire galaxy. So hopefully that gives you an indication of how we go about discovering exoplanets and the population that's out there. And then, excuse me, I'll go ahead and I think pause here in case there are any questions before I go ahead and show a few more videos.
Yeah, I don't see anybody running to the question and answer session, but the let me just ask you just a little setting a little context of history here. Am I right? The real research into exoplanets didn't really start until like about 1996, 97. Is that about right?
Yeah. So the first.
And what were you doing in 1960s, 1996?
Yeah, exactly. So I showed examples of the main ways that exoplanets are discovered. There's also a very specialized way that exoplanets can be found around very unusual stars. And so that was actually the absolutely first detection of a planet around another star. But the star itself was so unusual, it was called a pulsar. And these are the stars that are the remnants of supernova explosions. And so the first detections of exoplanets around some type of star, in this case a pulsar, those were made in the summer of 1991, which I remember quite well because I was working at the observatory as a summer student, the Arecibo Radio Observatory. And it was my supervisor who detected these systems. So it was really an exciting time to be a summer student at the observatory. And it had been actually quite an eventful summer because prior to these first pulsar planets, there had been an announcement of potential planets around a pulsar that had to be retracted because it turned out to be, it was just something that wasn't accounted for in the data analysis. It was the motion of the Earth that hadn't been accounted for. And so that was a really exciting introduction to astronomical research.
So is that when you decided that this was your field? Was that kind of the excitement that happened?
Actually, it took a while. So that was certainly an area I was always interested in. But then it was not until, so that was in like the early 90s, 91. But then it was several more years before the radial velocity technique, that first planet that we visited in the simulation. So that wasn't discovered until more like the mid 90s. Right. And it was these indirect approaches to discovering exoplanets that came first. So it was sort of the opposite of our own solar system, where first planets were discovered by eye. Then the next planet that was discovered that was not visible by the eye was discovered by imaging with a telescope, Herschel's discovery of Uranus. And then only after that was there an indirect detection of Neptune, mathematically based on its orbit. Well, with exoplanets, it was the opposite, where it was indirect detections first for many years, and only much later was the imaging, the direct detection. Only then had the technology advanced to the point where it was possible. So I've always been interested in imaging. And so it took a longer time to get imaging. First, I started with binary stars, then brown dwarfs, and then now planets.
It's excellent. I just think it's amazing. And yeah, let's. So I'm going to just invite the team to bring any questions up that need. I see the question and answer box is kind of starting to get some questions in it. So please just break in and ask as we go. And then I'll ask Jenny. So I think you got some other videos. I think you were going to show one of the. Well, tell us about the observatory that you're using. In
Yeah.
Chile.
So I thought you might enjoy next. I might even show it twice because it's a bit of a short video. And so I'll give the audience a clue to look to your upper left, and you might see something that looks familiar, but different at the same time. And so this will help you. You can see if you can understand where the observatory is based on that. So we'll next go to that video. You're seeing a video of the Gemini Observatory here. So with the hint to look to the upper left, see if you see something familiar. And then you see the observatory opening up. The light you're seeing in the sky, that's the moon. And this is an all sky camera that captures the night sky. You're seeing this spectacular view of the Milky Way in the upper right, and that's moving as the time is advancing. This is a time lapse simulation. So I'll go ahead, and you can all, in your minds quickly, before I tell you, think about where this observatory is located. And then I'll show the video again. And now let's look in the upper left, and you see Orion constellation, familiar but upside down. That's because this is an observatory in Chile. And you're also able to see the Magellanic Clouds up here, which you unfortunately only have a view of from the Southern Hemisphere. So this is a spectacular view of the Southern Hemisphere skies, in this case from mountaintop in Chile. And you're seeing this observatory has an 8-meter diameter of the telescope mirror. And so that's really important for these imaging programs to be able to have. This is one of the world's largest optical infrared telescopes. And so we need that when we're doing something as difficult as imaging the faint light of planets near very bright host stars. Okay.
And then just going on the infrared just a little bit, right? I think if I can characterize this particular research, you're looking for new solar systems, ones that are kind of hot, that haven't really cooled off yet. So you're finding solar systems, but they're not exactly like our old stable solar system. These are going to be young, hot, active ones, right?
Yeah, it's a way of studying the earlier history of our own solar system. So we can't go back in time with our own solar system, but what we can do is identify stars that are younger, and then we can search for planets around these younger stars. And there's both scientific interest in terms of studying younger stages of the planet formation and evolution process, but then also there's a technical reason to study younger stars. And that's because planets are warmest when they first form. And then over time, because they don't have a fuel source like a star, there's no fusion like in our sun, the planets just cool and fade with time. So that means they become ever more difficult to image as they become older and older. So we try to catch the planets when they're younger and warmer and more easily detectable. And we, rather than trying to observe them in the optical wavelengths like our eye operates at, we study the planets at longer wavelengths, which is where they emit more of their light. So these would be wavelengths that are more like they're a little in between those like nighttime cameras. Those operate at somewhat even longer wavelengths. So what we use are wavelengths in between like an optical camera and maybe one of those nighttime viewing cameras you might have some experience.
Sort of like infrared binoculars that you would use.
Yes.
Then back to the observatory. So Gemini, this is actually one of two. The idea was these are two matching telescopes, one in Chile.
That's correct. That's how it got its name. Yes.
That's how it got its name. And so what's the future? Do I understand correctly that they're renovating the one in Hawaii? You're going to move to use that one now? Is that
yeah? So exactly. So I'll show you images from a project that used this southern telescope in the pair of telescopes, the Gemini twin observatories. So first, we conducted a search for imaging planets and disks around young stars. And so the instrument is now being upgraded, and then the instrument will move from the south to the north. And so the observatory, or the site of the Gemini Observatory in the north, is Mauna Kea, the volcano on the Big Island of Hawaii.
Excellent. So do you have something to show?
Yeah, so should we go ahead and go to the
go ahead, and
from that program?
I'll ask the team if there's any questions in the background we can take as well too.
Okay, sure. All right, so next what we'll do is we'll go ahead and with that Southern Gemini telescope, the project that some of the ASU students, and actually it was part of a large international consortium, so a large team of astronomers, we all were very interested in searching for these young planets and disks around young stars. So what I'll show you next is we'll start off with our own solar system. So as the movie advances, we'll first see our view of, here's our solar system.
That looks really familiar.
Yes, yeah. So outside the orbit of Neptune, you're seeing what is called the Kuiper Belt. And so this is where, for example, Pluto is located. And so our own solar system is not the only system that has this ring of debris around it. And so what we'll do is we'll be visiting virtually again, but we've embedded real research images into our map here. So you get first a sense of scale of the region of space that we were exploring. So these are nearby stars. They're typically within about 500 light years.
And you call that nearby is 500?
Yes, that's actually very nearby considering the galactic scale. Yes, exactly. And so what you're seeing colored are the stars we searched. And now we've switched the color to the stars that have what you'll see an imaged dusty ring around them. And we'll go and visit a few so you can get a sense of what we see in these research images. So first you see a system HR 4796 with a ring-like structure where you can actually see the empty region in the central part. Now we visit another star, and what you see in this case is the orientation of the ring is more face-on. So we actually see much of the entire ring around this particular star. Now we'll zoom out to another system, and you'll see how the orientation impacts what we see. And we have to take that into account when we interpret our results. Now you're seeing a disk that's mostly edge on. So we don't see those gaps and ring-like structures, but we expect that the structure is still a ring. It's just that we're seeing the edge on view of it. And next we'll go to a system that's particularly important, because if you look carefully, you see that this edge on view, it's not symmetric on both sides. And we also know that that system has an imaged planet around it. So it's thought the presence of the planet has disturbed the structure, and that's part of what we're studying. And now you're seeing like a montage of all the research images of the disks around these young stars. And what we're exploring are things like, is the structure symmetric or not? Is there evidence that it's been gravitationally, if it's had gravitational interactions with other objects like planets, maybe planets that are too faint for current technology to be able to image. And so that's part of what one of my PhD students is pursuing as his thesis on this topic. So maybe I'll pause there in case there are questions on the studying the disks around stars. And then the last movie I have is a little bit of motions of orbits of some of these imaged planets.
No, those are actually fascinating. It's just as amazing to see these, because I can really picture for myself, just because they are flat, right? Flat and circular. I mean, these are just little systems coming into existence. I think that's absolutely amazing. And I think if you would, you might be wiser than I in this, but if you had asked me 20 years ago if we'd ever be looking through telescopes and seeing planets, I would say you're crazy. That's never going to happen. They're too far away. But you've made it work, and I think it's really awesome research. It's amazing.
Yeah, it's certainly been a culmination of a lot of effort. So it's a research topic that pulled from many different areas, and so there were a lot of contributions that had to be made on developing these systems to measure and correct for the turbulence of the Earth's atmosphere. So that was required to make the imaging high enough quality. And then a lot of work on understanding, which wavelengths would be best, there's a lot of technology involved in how to block the light of the star most accurately. And then a lot of data analysis work on once the images are received from the telescope, you don't necessarily see the planet immediately. It takes quite a bit of software work to be able to pull out that signal. It's not the case that the planets are so intrinsically faint that you would never see them otherwise. It's that they're so close to a really bright star. So the real problem is the brightness difference. Things like images of faint galaxies, those objects are intrinsically much fainter than the planets, but they aren't right next to a bright star.
That's right. Yeah.
So that's where the real challenge comes in on the technology side. And then from the science perspective, these are very different systems than what you are able to explore with those indirect techniques. When we saw discoveries from measuring radial velocity, so the spectrum of the star, or looking for transits, those approaches discover very close orbit planetary systems, whereas imaging discovers wider orbit planets more like where Saturn, Neptune, Uranus, and beyond, those regions of our solar system, that's what we can explore with imaging compared to well interior of the orbit of Mercury, which is where many of the indirectly detected planets are located.
Yeah, so that's something we sort of went fast and didn't point that out. But if you're in an indirect method and you're waiting to see the wobble, or you're waiting to see the transit, those planets have to be moving fairly fast, right? So you're seeing a transit every several days, not every year or so, I guess. So
yeah, that's right. And that's why the field of exoplanets has just had so many surprises. So the first being planets around pulsars, post supernova objects. The next was those very close orbits, because the types of planets that were discovered initially with those indirect techniques, those were giant Jupiter-like planets. And so in our own solar system, the giant planets are all at wider orbits, but then they were located, as I mentioned, inside the orbit of Mercury around these earliest discoveries. So that was a big surprise. And new theories had to be developed to explain the locations of planets in those orbits.
Yeah, that's how research works. That's absolutely amazing. Just fascinating to me. And it just seems like there's so far to go with this. I mean, there's so much of the nearby galaxy to explore, right? All the things you're going to find. I just think it's amazing. So it's fun to watch. Did you have another movie real quick?
Let's see, I have a movie to show that gives an indication of those orbit differences that we were discussing a little bit. So this may help get a sense of scale. So what you'll want to be cluing your eye into is take notice of the date in the images. So these are three different systems where the planets have been imaged. And so what we're able to do is piece together snapshots from different years. And so you'll see time advance, and you'll see the orbits of these planets about their host star. And what you'll notice is that it's only fractions of the orbits that have been able to be monitored, even though it's been many years of careful watching of these systems. So I'll go ahead and show the first one. So this is a system that is a star that's a little bit more massive than the sun. And you see there are multiple giant planets that have been imaged around this system. And so if I go ahead and turn time on, you can notice time advancing, and you see the planets moving in their orbit. So I can go ahead and show that again. This gives you a sense of scale. This 20 number, this is 20 times the Earth-Sun distance, just for a sense of scale. So what you're seeing here are planets that are in orbits that are out where objects like Uranus, Neptune are in our own solar system, maybe Saturn on the closest of them. So again, you see that the planets have moved parts, and the closest planet has moved the most amount of its orbit, just as we would see in our own solar system. And then these more distant planets, just a bit of their orbital arcs. But even you don't have to see the entire completed orbit to be able to estimate the period of the orbit. So this is the first of those systems that had multiple planets imaged. And then next we'll see a system where now you see the bar is 3 times the Earth-Sun distance. So this is now a much closer orbit. And so you'll see the orientation is also different. So here you're seeing the planet marching inwards. And there was hope that this would be a planet that was both imaged and transiting. but the orientation wasn't just right from our perspective from the Earth. So we didn't get the transit, but we can see the imaged orbit. And at this point, so I don't have an updated movie. At this point in time, the planet has actually moved to the other side of the star.
So now it's come out the other side? So
Yes, that's right. So the planet itself, unfortunately, we didn't get the transit, but there's a region around the planet called the Hill sphere, and that's the region of gravitational influence of the planet. So there were studies as the Hill sphere crossed in front of the star to use that to search for like other objects that were detectable within the gravitational influence of the planet. But I don't think those have turned up any like clear evidence of, for example, a really large moon or string or a disk of debris itself. But that's what astronomers were searching for during that transit period. Okay, and then what you see down in the lower right corner, this is now one of the nearest stars in the sky and is very bright. And it was known to have this ring of debris. So this is like what I was showing you those images of from our disk imaging survey. But this is one that was imaged with the Hubble Space Telescope. And so the purpose of this study was to image the ring. However, when they put together different years of data, so again, take a look at the year in the corner, what was noticed is that there was this little object that was moving. And so because it's at such a wide distance, so again, here's that 20 times the Earth's sun indication. And so this is now, you can see many times, 20 times. And so the orbit is a very long period, but even with those 8 years of data shown in the movie, it was possible to see that this object was making an orbital arc around the host star, that it's not just a background object, it's moving in the way you would expect for an object in orbit. So those are examples of these long period orbits. We don't get multiple orbits like you do with a transit or a radial velocity. And so that allows us to explore these wide orbit planet population.
It's absolutely amazing. Just absolutely fascinating. So, all right.
Okay.
All right. I think we probably should go kind of to, we have some poll questions for the audience. We're going to kind of ask them what they might think about the number of exoplanets. Got a little resource we want to show you. And so we can kind of go to the full screen view again, I think.
Okay, and then should I go ahead and do the stop share?
Yeah, go ahead. And so I think we'll just kind of have our faces up. So here's the first poll question for you. And Alicia, do you want to walk us through it? Or who's
Sure. So it looks like our poll questions have launched and our audience is already getting started. Our first question is, how many exoplanets are confirmed? 800 plus, 5,000 plus, 10,000 plus, or over 100,000? And then our second question is, how many exoplanets do you think there are in the galaxy? 10,000 plus, 100,000 plus, or 1,000,000 plus? So go ahead and cast your votes down below and I will end the poll and read the results in a moment.
Jenny, we have a pretty savvy audience, I think.
Yeah, it looks like it.
All right, I can end it now. It looks like a good majority of us voted and I'll share the results. So how many exoplanets are confirmed? It looks like 48% of us thought that was about 5,000 plus. So Jenny, Rick, do you want to confirm?
Yes, and keep in mind, this is a field that has ongoing discoveries, but currently the census is somewhat more than 5,000 planets. And then if the question had been worded a little differently, that's about, some of them are in multiple planet systems, like our own solar system. And so it's something on the order of 3,500 systems of planets.
Okay, I was going to ask because we don't always just see them, like, in fact, it's more rare to see a single planet, right?
It's
actually, maybe I'm saying that wrong. It's easier to find a single planet, but
yes, that's right.
Okay,
yeah.
I get it. Okay,
perfect. And our second question: how many exoplanets do you think there are in the galaxy? 61% of us said over 1 million. So, Dr. Patience, Rick, what do you think?
I'm going to let Jenny answer this one.
Yeah, exactly. So as you saw at the end of that first video of the simulation of the amount of our galaxy that we've been able to explore thus far, you saw that there's only this local neighborhood around the solar system. And so considering the volume of space we've been able to explore thus far, and then the volume of the entire galaxy, you would extrapolate the number to be, yes, very large, of over 1 million for the galaxy.
Okay, I'm going to ask if there's any audience questions we can kind of bring forward. And then also I have a kind of a final question for you too. So Alex, do we have anything that we want to share from the audience?
We do. We've had a lot of good questions, and we have some that we collected out. One of them, Stephen Schreier asked, are most of the discovered exoplanets in one region of our galaxy, or are we seeing them everywhere?
So that's a great question, and one that it would have been tough for you to see if I had more time to describe that simulation. Wait, I don't know if I can quickly get to the.
If you want to try to go back to this, right?
Well, it's probably difficult to see, but basically everywhere we look, we find exoplanets. And then it turns out that there are regions of the sky where more time has been spent searching for the exoplanets. And so for those regions, so there are particular lines of sight where we know about more, but it's because we have searched more in that area. So there isn't, maybe one of the few areas that has been searched relatively deeply that where we have not found a large population are in the globular cluster environments. That's one environment in which I think there have been somewhat fewer detections, but basically everywhere that's searched, we find population of exoplanets.
Excellent. Any more, Alex?
Yeah, and then Kimberly was asking, what's ASU's contribution to that 5,000 plus number? How many exoplanets have we contributed as a part of, and what's like the global kind of contribution in terms of that?
Yeah, these are studies that it's great to get a sense of the the field, and this is an area where a significant fraction of astronomers worldwide are pursuing some aspect of exoplanet research. A way to get a sense of that is that with the recent James Webb Space Telescope launch that many of you have probably followed, there was a call worldwide for astronomers to request time on the telescope. And this is very competitive. Everyone wants time on the James Webb Space Telescope. And something like 20% of the time goes to the field of exoplanets. So it's it's really active, very, there's a lot of interest in this field. And so for ASU in particular, one area that or areas that we're especially involved in, we're also very interested not only in the discovery of planets, but actually in the characterization of their atmospheres. So that's an area where with both, we have people working on the theory side of atmospheres, and then people working on the data side. And then also in the star-planet interactions, there's a lot of work at ASU in that area. And so it's getting this fuller picture of the understanding of the systems that I think that's really a vanguard area for ASU, in case you were curious about local exoplanet work.
Super cool. And so James Webb, I'll let Alex kind of give the news about when we might have some images, but it's still testing, it's still configuring. We're going to get new images soon, but I imagine it's going to be a while before we start to see some of the exoplanet research come in, right? So
yes, but it's certainly in that first year of taking
good.
data.
Okay,
yeah,
good.
It will
so
definitely
we might see exoplanets within the next months then.
Yeah, topics that are of interest. James Webb Space Telescope is not probably going to be used, certainly at least initially, for searches. That's a less likely topic, but for this more detailed understanding of the planets themselves.
So re-looking at things we already know about. So right.
Yeah, yes.
Assumes they already existence to tease out more information.
Yeah, exactly. To understand the properties of the atmospheres. There's a lot of interest in that.
Hey, I'm gonna, so we're going along, this is a fascinating subject. I wanted Armand just to show everybody a quick little resource because remember that question everybody had, like 5,000 plus. Armand, why don't you come up? There's a website, we'll put the link in the chat room. And so this is basically NASA's official website on how to count up. Do you have it ready? Hi, Armand.
Yep, I have it ready. Let me just share my screen. And yeah, this is the NASA Exoplanet archive. It's just exoplanets.nasa.gov. And if we go over here, we can see there have been over 5,000 confirmed exoplanets. There are quite a few.
1035, I see it.
Yeah,
Okay.
5,035. There are quite a few which are candidates for exoplanets yet to be confirmed.
So
And there-
candidates means that we've seen something, but like partial transit, partial wobble, we haven't confirmed it yet?
Yes, examples of how something's a transit, or I'm sorry, a candidate, but not a confirmed, would be if there are transits that suggest it's a planet, but then to confirm the mass, usually you follow that up with radial velocity to
Okay.
get the mass.
I get it. Okay.
Yeah.
Sounds super.
And yeah, this is just a really great resource. You can learn a lot about what exoplanets are, what the different types of planets, exoplanets that are out there. If you scroll to the bottom, you have some really great artwork, and you can explore some of the stranger and weirder exoplanets we've discovered so far. And my favorite part of this website is sort of going back to something that Dr. Patient showed earlier, which is a interactive 3D view of where we found exoplanets in our own galaxy. And you can see here we are, the sun is right in the middle of it, and if we back out all the way, and you can play with this on your own as well. If
And
you back out, you can,
Yeah, and those
Mhm.
directions where you see a lot of exoplanets, that's where there have been missions to specifically look at a point in space, and therefore you're able to detect planets at all distances along that line of sight. And so it gives you a sense of how many more are out there to be explored. Most searches are more local.
Excellent.
Yeah.
Super cool. Great resource. I've used this a lot. So we actually, over the years, we've had exoplanet shows and things like that in the Marston Theater, and we had to constantly update. Every time we got one done, we played it for several months. It's like, oh my gosh, well, everything changed again. So we added and did that. So we've been having to stay very nimble to stay ahead of the research and just be on point. So a website like that helps. We can just look before the show, and it tells us how many known planets are out there. So super cool. I love it. Okay, last question. We need a really quick answer. Sorry about that, but it's a tough question. Is Earth-like planets in an Earth-like orbit? Are we there yet? Are we close? Or are we?
Oh yeah, that's a real key long-term goal, to find an actual Earth-like planet, potentially around a sun-like star in an Earth-like orbit. And so we know from our own experience that would take a year to detect an Earth-like planet around a sun-like star. But if you search lower mass stars, then that region where liquid water can be present, what's the most basic definition of this
Right.
habitable zone, that occurs in much closer orbits if you search lower mass stars. So that's actually a big focus of current research, to be investigating these smaller, lower mass stars, to search their habitable zones, which are closer than the habitable zone around a sun-like star. And there are planets that are known in habitable zones around a range of stars. And then a subset of those are known to be rocky planets, as opposed to like giant planets.
That's great.
And
Okay.
so, yeah, that's certainly, that's like
We're
a key
closer.
goal.
It's like tantalizing. Just sort of like-
Exactly. Yeah. So there's the beginnings of that. And that's in part where then exploring those atmospheres, when we find those objects, to understand, well, what type of planets are they really? And so that's, yes, you've keyed on a very important aspect of this research.
That's great. Well, super cool. Jenny, it's always a pleasure. I have watched you teach over the years, and you're just so engaging, and students love your work, and it's always exciting. I mean, this is the groundbreaking. This is kind of research that is really just right on the edge of discovering new life and new planets and all that kind of stuff. We're headed there, heading in the right direction. So.
Yeah. Well, hopefully all of you enjoyed a little overview, and it's certainly something to continue following in the news and on articles like Armand showed you. That'll be a place that you can be on the lookout for more new results.
Excellent. Well, super cool. Well, thank you very,
All right,
very
thank
much
you.
for joining the show, and I really appreciate it. Thank you. All right, everybody. So next step is we just have a bunch of quick little updates, and we're running a little bit behind, so I'm going to go really, really fast. I wanted to show you what I was doing last week, and oops, that's the wrong thing to show you. So hang on just a second. I'm going to have to do a different little overlay here. Screen share options, secondary display. Here we go. And so let me just make this really bigger so I can show you what's going on here. What I did is I sort of did a little road trip, and a part of it was business, and that's the important part I want to show you. I also have proof that I got up before sunrise, at least a couple of days. And that's sort of, this is the sun rising over Crown Point, New Mexico. And that was one of my main stops. We actually have a partnership, ASU, and what's called Navajo Technical University. So if you've never been to Crown Point, it's on the Navajo reservation. And we've started to do a little project with them. So I wanted to kind of show you a little bit about what's going on. The university, or the technical school, is in the background. You see the sort of, Crown Point is really high, it's 7,000 feet, but it's very, very dry and very desert-like conditions. They happen to have this dome, and it's been in disrepair and out of use. So we're sort of like just kind of evaluating it to see if we want to bring it back into repair. We worked for a couple of days. This is in a classroom, sort of like working with a couple of professors at Navajo Tech. I was there with a friend, the guy in the yellow shirt, it says Arizona State on it, is Tom Mosden. He's in our program. And so he and I are sort of this advanced party. We're actually showing these students how to use some telescopes and how to set up to do their own star parties. So this is before dark, a little bit after sunset. And so we're out here, and little did we know, we sort of like talked, okay, it looks like it's going to be a good night. Let's set up some telescopes. Let's get out there, invited everybody back. It wasn't dark until after 9. And so little did we know, the announcement went out to the community. So we had all these people, all multiple ages. These are all Navajo. This is on the Navajo reservation. And they just loved it. And so what we're doing is we're setting them up. We gave them these 2 telescopes for their use. They bought another one that's sort of like the one way on the left side of the screen. And they're kind of just, we're encouraging their students to learn how to do this and do the public engagement and the science communication, sort of like we do here. And so I think this is really cool. Some of their students will come visit us in the future, and some of those students will, and then we're going to send some students back to here in the future. So we've got this really wonderful exchange, and it's going on. Here is some of that scene, and you can't really see it here, but there's the moon. There is a planet. It is Saturn, is way up at the top of the screen, kind of a little bit to the right of the moon. Jupiter is sort of towards the other end of it, on the bottom end of the moon. I got up here before sunrise, and I kind of watched the sunrise, but it was a little too late to see the planets. After Crown Point, I moved on. This isn't Crown Point. This is Southern Colorado, and this is something very, very different. We were doing this thing where we're actually studying an archaeological ruin. So this is called Escalante. It's a pueblo. And you see the shape, that round shape in the beginning is a kiva that is embedded in this particular thing. And everybody that's in a sort of a tan shirt is part of our team. I'll show you some other images. I got to go pretty fast. You don't get to take a ladder and go into a kiva, just like you can't do that, except the gentleman there in the dark is the archaeologist for Canyon of the Ancients. And he allowed us to go in. We were taking some measurements and doing some photography inside the kiva itself and creating 3D models and all this. stuff. Some of the data hasn't been sort of totally done yet. You can see a lake in the background, that's Lake McPhee. It's a beautiful area, really great place. This is part of one of what I was doing. I was kind of doing some survey work and doing transects just to sort of like look at the wall angles and how they sort of land on the landscape. We're trying to derive sort of, what kind of cardinality, the directions that these things were using, or were there astronomical sightings that they sort of used to site their buildings and things like that. A little bit undetermined yet. Here's the crew. I'm on the left over there. All of those people are part of the deal. Here's some, I'm in the Kiva now. I'm kind of doing my photography and I'm being watched over by all these people. Some of you might remember Mary Oaxaca. She's the fourth one over from the left. She was a guest on our show. She's from Santa Clara Pueblo in New Mexico, and her husband is in the center of this scene. And they were actually integral and part of our team. So this was really great because we did the field work at the Kiva. And then afterwards, we were able to kind of go back to the house and sort of like open up some beers and talk about sort of the native context to sort of these alignments and these places, what these things mean, how does this thing find itself on this hilltop and all that stuff. It was absolutely beautiful. That's the screenshot you saw behind me, but this is a nighttime view from that same Pueblo. That's Gemini, the twins are sort of up in the middle of the sky, and Procyon, and we've got a telescope over here. I was helping a park ranger actually set up a scope, and it's something they haven't done since COVID. He's new to the program and new to this place. So we're getting them ready for a public star party. And then I got up early in the morning here as well. There's the eastern horizon line. And here you see a little close-up of the sun rising over some of those mountains. I just felt very energized. The fact that I'm here at this particular place, at a place where people were here 1,000 years ago looking at exactly the same scene. And I was able to capture it with my camera. It was really, really fun to do. The other technical part of this is we're dealing with imagery and recording and just testing that we can predict. So I predicted that the sun would be there with some technology that we can share with amateur astronomers and people in the future. And then you can go out and verify it. Sure enough, the sun rose, and I felt responsible for it that day. So as I was leaving, I kind of ran into a little bit of a roadblock. And then the last image I want to show you is actually from this morning. We had some visitors at the center. I said you could come visit us, and here's real life. So these people are from Friendship Village, and they came through, got a really wonderful tour this morning. They're standing on the 3rd floor of our building and looking up at a stairwell, and got a picture of them. And we told Friendship Village people that if they allowed us to take the picture, that they could watch the show tonight and see themselves on the screen. So you can wave at yourselves. There you are. So that's really great. So find a way to get a group together and give us a call and come visit us. That's really the message there. Thank you. That's really just a quick update. I wanted to say we don't just kind of rest in the summer. Once school's out and the students are sort of, kind of out of our hair a little bit, it gives us a chance to do some of this stuff, do some research, go out to the field. So this is a very typical thing that we do at a university basis. And I just love setting up those relationships with these partners, not only in Southern Colorado, but also on the Navajo community at Navajo Technical University in Crown Point. It was really great. All right, I'm going to move on. I think we go to Alex next. Did I get that right? We talked about this.
Nope, I'm last.
Oh, you're last. Okay, Alicia. Yay.
It's me. Hello. Thank you so much. Yes, we're going to do a lightning round of current events. So you may have noticed Monday night or Tuesday morning that Earth passed through the debris left behind from a broken comet that actually broke in 1995. And so we weren't sure if we were going to be able to see it. It was dependent on if the fragments were moving fast enough. And it turns out that we were able to see it. So it does help that we had a new moon to keep viewing optimal, but still we were very excited about this opportunity to view a meteor shower. And if you're wondering where this photo was taken or who it was taken by a regular on our show, Kevin O'Donnell. He's an astrophotographer, and he took this in Sedona during the meteor storm. And so this meteor composite consists of 33 photos over 3 hours, including a tracked stack for or excuse me, a trapped stack of the Milky Way galactic core and dozens of meteors. So thank you so much, Kevin, for sharing this photo with us. We're very excited.
I love Kevin. He always delivers. He just sent us this morning, so we sort of like throw it in here. And so this was, we didn't know actually what this meteor shower was going to look like. Had no idea, and so I'll be darned, it worked. That's great.
It was beautiful.
Yep, thanks.
But that's it from me. I'm going to go ahead and pass this next section of current events off to Kimberly Baptista.
So good evening, everybody. Let's see if I can make the slides move here. So last week on Friday, we had a couple of special guests visit the School of Earth and Space Exploration. We had NASA Administrator Bill Nelson, who's also a former senator, and Senator Mark Kelly. They dropped by for a visit, and they got to see all the things that we are working on, which is more than 20 space missions. And they also got to take a tour of our meteorite vault. And they went ahead in the, I'm going to have Alex share a video. They got to ride in a lunar rover. And Rick, you might be able to add a little bit more about the rover.
Yeah, this particular rover was built by people on ASU campus, and it really is. It's kind of the next technology. So what we did is, or what workers at ASU engineers did, is they built this rover, and if you can imagine, all four wheels turn in all directions. So not like your car where half the wheels are fixed and the others turn. In this case, all four of them. So literally it can spin around on itself, or you can spin the wheels and actually drive sideways across the landscape. It's really, it's a lot of fun. And obviously these guys had a lot of fun doing it. Kim, tell me like what this was like, because we didn't know they were going to drive it, right? They got in and off they went. Is that what happened?
Well, we told them that they could do a photo op, and then and then Mark Robinson, who oversees this project, he's like, do you want to take her for a ride? And they took off. So
Okay.
I think, both of them being astronauts also, they probably have some knowledge of how to work some of these.
I know, but they've never seen this car before. That's amazing. So that's really
so it was really nice to be able to have the person who runs NASA stop by and be able to see, hands-on, like what we're doing, talk to our students, talk to our researchers, and get to hear about it. And then also, Senator Mark Kelly, who's also an astronaut, and is big on, partnerships with, universities and private companies and whatnot. So it was nice to be able to really highlight what we do in the School of Earth and Space Exploration. And
great for all of you to meet them too. So this came up kind of late, and I already had that other trip. So I'm digging in or imaging and measuring a Pueblo in Colorado. You guys are playing with senators here back at campus. So good for you.
So it was a nice visit. It's always nice to be able to show, all the amazing things that we're doing and our amazing staff and faculty that we have. So, and with that, I'm going to hand it off to Alex.
Yeah, we're back to Alex.
Yeah, so I'm going to talk about just a very amateur part of astrophotography. We talked about Kevin O'Donnell, who's been on this program a bunch before, and talked about his astrophotography. People are always asking, what equipment do they need? Fancy cameras, telescopes, and those work great at getting beautiful images, but there's a way to do astrophotography with just the thing you carry around in your pocket, just your phone. And so that's what I have a little segment about. We've kind of thought about and dabbled with this concept, but let's talk about astrophotography, because yes, you can get really expensive telescopes and imaging equipment and mounts, but these phones are developed now to the point where they have long exposure modes, they have better sensors for nighttime, and they're getting actually optical zooms now. It's not just digital anymore. And so they're becoming more and more capable with astrophotography, and so we're going to talk about that. Last week I was actually in Jack and Hole, Wyoming. I was up in Teton National Park, and I actually took this on my phone. It's at our campsite. You can kind of see a bunch of stars, one very nice dark sky. There was hardly any light, but you can actually start to see kind of the band of the Milky Way right here. I'm pretty sure that this is the star Polaris. I don't remember exactly, but I know it was northwards and there was a star there. But this is just taken on my phone. This is the phone I have now. This is one of Apple's new iPhones, and they got new long exposure modes that take a bunch of different exposures and then stack them together to create these images. And so this is the thing you can do. Now I will say you're not going to get great high resolution images of nebulas or like the Pleiades or small star clusters, because these are really distant small objects, and these phones don't really play to the strength of distance. What they work at great is kind of wide angle landscape portrait shots like this, and now they're getting better at nighttime photography. So if you want to start taking pictures of the night sky with your phone, remember what it's built for. Play to its strengths. Look at the lenses it has. Some of these are getting even more impressive optical zoom, so you might start to get to the point where you can maybe start taking really great pictures of the moon without needing telescopes. But just using your phone, these nighttime sensors are really incredible. In fact, this one actually, it has a setting on it with multiple modes. This longest exposure mode actually requires it to be mounted on a tripod. You can't handhold it. It won't let you access this. Well, what I did is I just had a camping chair with a cup holder, and since I didn't have a tripod for my phone, I just kind of wiggled it in there to the point where it wouldn't move, and then it let me access the full settings. So just play to the strengths, kind of adapt. And remember also, there are really cheap mounts for these phones that mount on telescopes and spotting scopes, and that can also increase your zoom resolution and kind of the distance and objects you can see. So you don't need to buy an expensive telescope. You don't need to buy an expensive DSLR camera. You don't need an expensive star tracker. Just work with what you got, and you might be able to take pictures like this. And ultimately, it's just going to help you understand and appreciate the night sky more. But I guess if you really want to take great pictures, then reach out, go watch all the episodes we've done with Kevin O'Donnell and all the stuff he talks about with his equipment. But just let you know, these phones can take great pictures now, and just go out there and explore with them if you ever get the chance.
Thanks, Alex. Alex, I'm going to just pop a question for you, a totally different subject, but what does ERO stand for anyway?
Oh, ERO, right. So we've been talking about James Webb and exoplanets, and it was announced today that James Webb's ERO will be dropped on July 12th. That's the early release observation, or that'll be the very first image science data driven and captured by James Webb in July 12th. That'll be it's announced. That's kind of what we figured it would come around, either late June, kind of early July. That's going towards more mid-July, but it looks like it's going to be kicking out images around then, and that'll be just historic landmark, and hopefully we'll get a lot of wonderful images to look at and share with you all in this program.
We will share it, absolutely. So this is just, if people have been following, we've been looking forward to this moment, and just got noticed today. It just kind of came through this morning. We all got emails from the team, sort of said, yep, here's where we're going to see the first images. So yeah, some telescopes call that first light. So there's been a lot of testing, been a lot of stuff. We know this telescope works, and now we'll actually see some real images. That'll be super cool. Good.
Very exciting.
All right, Alex, thank you very much.
Thank you.
Everybody, thank you for hanging on. We've been a little long. We're going on about 6 minutes after the hour. Sometimes that happens. And so I'm just going to kind of wind down and say goodnight, but I want to invite everybody to kind of rejoin us 2 weeks from now in Wednesday. The feature is going to kind of be back to planets. We're going to talk about sort of when we get to see them in the evening sky, what has to happen for all that to happen, some things to look for with sort of, what planetary systems are going to be best positioned at what times for the rest of our year. And we're going to do that. So that'll be our main feature, but as always, we'll have updates on some other things. I hope that we actually have some more, like what are we doing during the summer kind of images. And so I think we'll keep that up. It seems to be a good feature. And so we'll kind of give you a little sense of what's happening around campus, even though classroom's not in session. So thank you very much. Thank you to the team. Great show. Thank you to Jenny Patience. She was amazing as always. And we've learned a lot about exoplanets today. We'll see you in 2 weeks. Thanks everybody for joining today.